Section 8.6, log functions. This is quite a large section, but by the end of this section you should be able to recognize various log graphs, describe transformations of a particular log function from the standard log function, sketch various log functions, better understand the inverse relationship between exponentials and logs, and finally use log functions to model real-life situations. So that's what we'll be covering in this section. To begin with, I'm just going to focus on the connection between exponentials and inverses. So this graph here, f of x equaling 2 to the x, is an example of an exponential where we've got base 2. So you can see it's that increasing curve here with an asymptote at y equaling 0. Notice it covers through the point 0, 1. And if I moved for x equaling 1, then if I substituted 1 into this rule, I'd have 2 to the power of 1, which would be 2. So there'd be another point here where my cursor is at 1, 2. We know with inverse graphs, it's the original graph just mirrored in the line y equaling x. So you can see that we've got that curve. And if we mirror that curve in the line y equaling x, we'll get this. Now I'm telling you that y equaling 2 to the x, its inverse is y equaling log base 2 of x. And let's look at that shape. So this time what we see is that we have an asymptote at x equaling 0. And now instead of covering or coming through the point 0, 1, it comes through the point 1, 0. That's because the x and y for inverses just simply interchange. And instead of covering through the point 1, 2, it comes through the point 2, 1. So that point there at 1, 2 has moved to 2, 1. This point at 0, 1 has moved to 1, 0. So the x and y's have interchanged. But look at that shape, it's very different. Remember, inverses undo each other. So in the same way as 2 times 3 equals 6, 6 divided by 3 equals 2. So timesing by 3 is undone by dividing by 3. Sine of 30 degrees equals 0.5. Inverse sine of 0.5 equals 30 degrees. So the inverse sine undoes what's taking the sine of an angle does. 2 plus 3 equals 5. The inverse of adding 3 is to subtract 3. So you can see if I start at 5 and then take 3, I'll get back to that too. So an exponential, its inverse is the log, and look at that log shape. That's that standard shape. So now let's concentrate on 2 examples of log graphs. Here I've got log base 10 on the left hand side, and here I've got log base e. You can see the basic shape, and it's probably a little bit too difficult to see here, but the curve goes getting very, very close to the y-axis, coming through, passing through the point 1, 0, and then increasing along. And for here we've got log base e. Remember that e is simply Euler's number. So Euler's number is a number that occurs a lot in science, and it's approximately equal to 2.71. Again, you can see it's exactly the same kind of shape as on the left-hand side. Again, it cuts through 1, 0, but now what it cuts through is this position here, e, 1, which is approximately 2.71, 1, and then increasing. So as x increases, y will increase. That's the same for both graphs. And the first point here that's interesting for us on the left-hand side graph is 1, 0. The second point is 10, 1. So the base is 10, so you can see there I've got 10, 1. The base is e, so I've got e, 1. And that will always be the case. You'll also notice that we don't get on the negative side of the x-axis in both. And what we see is x increases, y increases. So as x approaches positive infinity, y approaches positive infinity. As x gets closer to 0 from the positive side, then y will be getting closer to negative infinity. And we have vertical asymptotes at x equaling 0 for both graphs. Talking about domain and range, our domain, the x values that we can have, are x being greater than 0, not equal to 0, but greater than 0. Or if you like, it's r, the set of all real numbers, plus. That's shown here. Our range, we can have from negative infinity all the way up to positive infinity. So we just write that as being r. Now, the transformations that we've spoken about before to describe any basic graph are applied to log graphs as well. So if we've got the standard y equals log base a of x, and it's transformed to y equals capital A log base a of this expression here, where a, the base, is greater than 1, then we can use these different descriptions or transformations to describe what's going on. Just a reminder, this capital A, we take the magnitude of that, so we ignore the sign, and we have a dilation factor parallel with the y-axis. So in other words, every y value has been multiplied by the size of that number in front of the log. What's the effect of the k, the value immediately in front of the x? Well, we'll be dilated by a factor of 1 on the magnitude of k, 1 on the size of the k, so we ignore the sign again, parallel with the x-axis. So every x value has been multiplied by the size of 1 on k. Talking about the dilations, reflections, if a is negative, will be reflected in the x-axis, so every y value is multiplied by negative 1. And if k is negative, will be reflected in the y-axis, so every x value has been multiplied by negative 1. Translations, the c, the part in the end, if it's positive, we're moving up c units. If it's negative, we're moving down c units. And then the horizontal translation, take everything that's inside this bracket, make it equal to 0 and solve for x. If we get a positive, then we're moving in the positive direction along the x-axis. If we get a negative, we're moving in the negative direction along the x-axis by however much x is equal to. Alright, our first problem. We're going from the standard y equals log base e of x to become y equals 2 lots of log e of 3 minus 4x plus 5. So, firstly, dilation factors. We've got a 2 in front of the whole family function here. So 2 lots of log e of 3 minus 4x plus 5. So we're dilated by a factor of 2 from the x-axis, or if you like, parallel with the y-axis. That is, every y value has been multiplied by 2. We've got a negative 4 directly in front of the x. So this tells us we're dilated by a factor of 1 on 4. I ignore the sign, so it's 1 on 4 from the y-axis. So every x value has been multiplied by a quarter. Reflections, because of that negative, I'm reflected in the y-axis. So every x value is multiplied by negative 1. I am translated 5 units up because it's positive 5. And now what I do is take what's inside this bracket, make it equal to 0 and solve for x. So 3 minus 4x equals 0, 3 equals 4x, 3 quarters equals x, and that's positive 3 quarters. So I'm shifted right 3 quarters of a unit. And of course right is positive along the x-axis. If we're considering sketching, then we start off with our basic shape. So the basic log graph, you can see is in green here. I have a negative x coefficient, so there's a negative number right in front of the x, so that means I'm reflected in the y-axis, so now the graph should look like so. Vertical asymptote, take the stuff that's inside the bracket, make it equal to 0, solve for x, so I get x equaling 3 quarters. My y-intercept, I simply substitute x equaling 0 into the function, and I get exactly 2 lots of log e of 3 plus 5. Now I know that that's approximately equal to 7.20, and that's evaluated on our CAS, and that just helps me do the sketch. Of course, when you provide that particular point, you should find the exact, or you should provide the exact values, so that line there. X-intercept, we make y equaling 0 and we solve for x. So substitute y equaling 0, divide both sides by 2, and so I have negative 5 on 2 equals log e of this. And now I rewrite it. In fact, what I do next is have e to the power of both the left-hand side and the right-hand side. So that's in effect doing the same thing. And so I have e to the power of negative 5 on 2. Of course, e to the power of log e just leaves me with 3 minus 4x. I take 3 from both sides. And now divide everything by negative 4. So that's my exact value, which is approximately equal to 0.73. And finally, here's my sketch. There's the asymptote. And there's all my values. You can see I've got that 3/4, so that was shifting it that way. So that's why I've got my asymptote at x equaling 3/4. And it's making sense. I've got a positive x-intercept and I have a positive y-intercept. So what I have here is reasonable. And notice that I give it as an exact point in both cases. So that position is here and that position is here. Just this manipulation of the x-intercept, we'll work on that a little bit more as well in the next particular section of our notes. So that step of going from here to this line, just saying, okay, let's have e to negative 5 on 2, let's have e to log e of 3 minus 4x. That'll be daunting because you're seeing this for the very first time, but in our next section we'll do a whole variety of these kind of equations, solving for x, and it'll make a lot more sense, as maths usually does, after you do various bits and pieces. Alright, so this time we've got f of x from here. I don't need to state the transformations, I just need to be able to sketch it and state the domain and range. So what I've got, basic exponential, like so, but I've got a reflection in the x-axis because of this, and also have a reflection in the y-axis. So that, because of the negative 3, is going to become this, and then that is going to be reflected in the y-axis to become that shape there. That's what I should get. Vertical ASCII, 1 minus x, make it equal to 0, solve for x, so I have x equaling 1. X-intercept, make y equaling 0. I add 3 lots of log e of 1 minus x to both sides. I now take the 3 to the top. And in this move, I've got e to the power of the left-hand side equals e to the power of the right-hand side. And the reason I do that is so that this e to the power of log e will cancel to leave me 1 minus x cubed equals e squared. I now take the third root of both sides. And remember, when you take the third root of something, it doesn't have a positive and a negative version, it just has the third root. It's just one solution, not 2 types. I subtract 1 from both sides. And now finally I multiply both sides by negative 1. So if I do that, the negative x becomes x, the negative 1 will become positive 1, and this version here will be the negative. And that's approximately equal to negative 0.95, evaluated from the CAS, of course. Y-intercept's a lot easier, just simply sub x equaling 0 into it, and I'll get exactly 2. So given that basic shape like so, then here's my graph coming through, and it'll continue on like that in that shape. Y-intercept, X-intercept, horizontal ASCII, and to be honest with you, I haven't answered this question correctly. So I need to state domain and range. So there's no domain restriction on it, so this will continue on indefinitely that way. So as X approaches negative infinity, Y will approach negative infinity, but there is a vertical asymptote here at X equaling 1, so I know my X values can't go along that way, but as X approaches positive 1, the value of Y will be approaching positive infinity. So straight away my range will be R, set of all real numbers, that is it goes from negative infinity all the way to positive infinity, but my X values that I can have are X being less than 1. Alright, not equal to 1, but less than 1. Alright, so we've already spoken about that connection between logs and exponentials being inversely related. Just a reminder, there's the two graphs there. So we've got the exponential y equals 2 to the x, and the log y equals log base 2 of x. So all the points on this curve, the x and y simply interchange all these points to become this inverse graph here. So as an example, 0, 1 becomes 1, 0, and the point 1, 2 becomes 2, 1 for the inverse. Graphically, you can see that this y equaling 2x, the mirror of that forms the inverse, log base 2 of x. So that there has simply been mirrored in the line y equaling x. If we were to find the inverse of y equaling 2 to the x, this is our technique. We've got f of x equals 2 to the x. I rewrite it as y equaling 2 to the x. Because the connection between inverse graphs is that the x and y simply interchange, for my rule, I'm going to interchange x and y. So instead of writing y equals 2 to the x, I'm going to write that x is equal to 2 to the y. I now want to make y the subject, so I want to get y by itself. So what I'm going to do is take log base 2 of both sides here. So the reason I've chosen 2 is because if I take log base 2 of 2 to the y, I'll get that. The y will come down, and then log base 2 of 2 was just simplified to being 1, which is great. That's what I want to achieve. So that's why I chose log base 2. So I take log base 2 of both sides, so I've got log base 2 of x equals y. So finally, the inverse of f of x is here, which is log base 2 of x. Remember that f to the power of negative 1 of x just means the inverse of f of x. Alright, let's look at some models. So the Richter scale. The Richter scale is one scale. It's a logarithmic scale, but it's a way of measuring the size of earthquakes. One particular technique, the magnitude, is equal to log base 10 of x on A, where x is the reading of the earthquake 100 kilometers away, and this must always be in millimeters. A is a constant, and that's equal to 0.001. Okay, so for this particular model that will give us a Richter scale, this little a is 0.001, and x is that distance measured in millimeters. Let's look at an application of it. So in San Francisco, there was a famous earthquake. It had a seismographic reading of 7.93 meters, 100 kilometers away from the epicenter. So the epicenter, of course, is where the earthquake started. What is the magnitude correct to one decimal place? So what is it on the Richter scale? So A is 0.001. X, the distance, is 7.943. That's what it measured in meters. And we need to convert that to millimeters. So, of course, 7.943 in meters is equivalent to 7,943 millimeters. So write it down in terms of that. So now what I've got is log base 10 of this very large number, 7,943,000. And if I evaluate that, then I come up with 6.8999, or approximately equal to 6.9 on the Richter scale. So the key to this is that the X figure, that seismographic reading, no matter what unit of measurement is given to you, it needs to be inputted as millimeters, and the constant down the bottom is 0.001. So there's a few questions in the text which get you to do that. Alright, the population of a species of frog in Lake Guthrie is declining due to an unknown cause. The number of frogs T weeks after the first dead frog was found can be modelled by the equation P equals A log base E of T plus B. 1 week after the first frog was discovered, the population was 1,000. The population was 800 after 5 weeks. Find the values of A and B. So, we know because of 1 week after the first dead frog was discovered, the population was 1,000. So 1 week, 1,000. So that gives us a point there, 1,000. Here's the model. Let's substitute T equaling 1 and P, the population, equaling 1,000. So log base E of 1. We know log of any base of the number 1 will always be a 0. So this whole first term will collapse to become 1,000 equals B. We have a second bit of information. The population was 800 after 5 weeks. So T equals 5 and P equals 800. Here's our function. And instead of writing in B, we know that B is equal to 1,000. So let's put 1,000 in there. Let's make use of this point. So when T is 5 weeks, the population is 800 frogs. So 800 equals an unknown A log E of 5 plus 1,000. We take 200 from both sides. We now divide both sides by log E of 5, and I get A. So A is approximately equal to this figure here. So I've now found the two variables that I need, and of course you'd need to do that on your CAS to get that figure. B, find how many frogs there are after 10 weeks. So now I can write my population function where A is that figure and involves T and B is this. Let's substitute T equaling 10 and I'll get to the nearest frog 714 frogs. So that's just using my CAS. C, find to the nearest week how long it would take for the population to fall to 300. So here's my population function, and I've set 300 equaling that. Now in my workings here, what I've done is did it all by hand, then just did the arithmetic calculations on my CAS. So you can see I've subtracted 1,000 from both sides. Then I've divided both sides by 124.2 or negative 124.27. Then to get rid of this log E, I've just simply said let's get the left-hand side. Let's have E to the left to the power of the left-hand side equaling E to the power of the right-hand side. The right-hand side will just collapse to being T, and so I get 279 weeks. Of course, at this stage here, I could have just put that into my CAS and solved for T. That would have been quite fine, and indeed less likely to make a mistake. Alright, D, just drawing a sketch of it. I know that I've got that basic shape happening. The reason for it is that I've got a translation up of 1,000 but I've got this negative here at the very front of the graph. So that means I'm going to be reflected in the x-axis. So it's going to be coming down like so, but then shifted up. So my points, and of course the population is decreasing, so it shouldn't be too much of a surprise, but I've got 1,1000. That's my starting point, going through all the way down. And what was my E asking me? So there's my sketch of it done. How many frogs would there be after 20 weeks? Use your graph. 20-week mark and go across. So look, you're not going to be asked this kind of a question and just have blank paper to put it on. What would be happening is that you'd be given a scale, say like an exam 2 kind of question or a part C on a test. You'd be given a set of scales, and then you would have to finish off the graph, and then you'd use that graph to find out a value. You can see there's a